Similar to the last activity, now we're going to take a look at state space solutions. And what we're going to do is we're going to claim a solution. So I'm just going to go ahead and give you this solution. And I just want you to get some practice becoming familiar with what this equation means and what it says and kind of how it's written. So I'm claiming that this is a solution. We kind of already see from class 8 that we have a piece that looks like essentially what we had in the homogeneous case. So that kind of already looks like we're going in the right direction. And now we're adding this piece that's due to the input. And so what I'd like you to do is show that this is indeed a solution. And so what is, remember, showing that something is a solution, just like we did in those first order and second order equation examples, is that you take the solution and plug it into the equation. And if it satisfies that equality, so if this is indeed equal, then it is a solution. So what that means is you have to take a derivative, a time derivative, to find x dot based on this solution. And so one of the things that you'll need to look at is we can use this Leibniz integral rule. You may not have seen this for a while, but essentially it says that if you have something that you're going to take the derivative of, so this quantity here that you're going to take the derivative of, and it has integration limits that could depend on the thing that you're taking a derivative of, that you need to pay particular attention. So what you're going to do is you're going to evaluate this integrand here, f, at this value and take the derivative of this limit. And then you can do that on the lower limit, and then you finally take the integral of that derivative. And so why is this going to be useful? It's not necessarily going to be useful for this term. This one you can take the derivative of directly using your knowledge of matrix exponentials. But this one, this is where this integral happens, and you notice that we're going to take a time derivative. So we're going to be taking d by dt of x, and x is a function of time, and that means that you're going to make d dt of this integral 0 to t. So you're taking a derivative with respect to t, and that t is up in that limit, and so that's why you have to be particularly careful. Notice that this formula that I've tried to show you here is particularly a bit tricky in the fact that here the thing you're taking a derivative is x, and here the integrand is with respect to t. Up here, this is the integrand is with respect to tau, and the thing that we're taking a derivative of is with respect to t. So this notation is a little bit confusing, but it's good to practice. Just because we're using different variables here doesn't mean that this says something not applicable. So you need to make sure that when you look at the t here and the t here in this formula that I've written out here, those correspond to the x's because that's what role they play. And this t that's here, those correspond to the taus that are here in this expression. All right, so then finally the last bit is to just go ahead and figure out what is the output y of t if this is the solution to x. So we're finding x here, so it has all to do with this equation. So then what is y if this is the solution to x? So go ahead and pause the video and take some moments to attempt this, and then we'll go through the solution. Okay, so we would like to prove that this is a solution. So what we have to do is we have to first calculate the time derivative of x of t, the solution that we're claiming, in order to plug it in here. So we can go ahead and plug in x directly here, and u is just u. So the key the tricky part is to calculate x dot. And so we're going to calculate d by dt of x. And so first we take the derivative of this piece. That piece is simply just the rules for matrix exponentials. So the matrix A comes down in front as we take the derivative with respect to time. X of 0 is not a function of time, so that just is a scalar, or it's a constant. It's a vector constant, maybe. So then we're going to take the derivative of this expression, which has that integral in it. So the first step is to take the derivative of this endpoint. So that's the derivative, that's d by dt of t. And so that's simply just 1, so that's nice. And then we evaluate the integrand where tau is equal to t. So now we're going to plug in where tau is equal to t. That makes this exponential. Tau is equal to t up here. That makes this exponential just simplify to the identity. Leaves us with bu, and then tau is equal to t. So that gives us this term down here. The next step is that we're going to now do the same thing with this integrand limit. In that case, it's a constant, so this derivative is 0, so we don't have to worry about this whole term. It goes away. And then the last piece is to take the derivative of the integrand, again, with respect to t. So that's the thing that we're interested in, with respect to t. And so that pulls down, again, a factor of a from the matrix exponential rules. And so now we just have to write this. So we don't exactly know what that is, but we have a trick to figure out what that is. So we just go ahead and write that down here, and we'll go ahead and pull this a out in front. And so what we want to show is that this is equal to ax plus bu. And so one way would be to write out ax plus bu. Another way is to realize that if we put this term, the first and the third terms together, and factored out a, what would be left, this e to the at x0, and then this whole integral would be exactly what we claimed x would be. And so that allows us to say that those two terms together are simply just a multiplied by what we claimed x was. And then what's left over? Bu of t. And so that is exactly what this differential equation says, and so that means that we've actually go ahead and solved it, and so this x of t is a solution to this differential equation. And so that gives us what x is, and so if we wanted to know what y was, because y is this, usually for us it's the scalar output that we're interested in, we're going to plug this vector x, remember that's a whole vector, plug that in here, and to compute what y is. So that means that y is c e to the at x0, and essentially you just plug this c in front of both terms, and then if you have this term, this d term, then you just tack that on. And so that's what y looks like. So one of the consequences of this is it allows us to connect the state space solution that we just presented with all of the transfer function motivation that we began this particular class with. So again, this is the solution that we just proved is true, and that's for the output. So if we wanted to know what the impulse response was, remember that's the response y of t when we have 0 initial conditions and the input is a delta function, is that impulse. So if we were to stick that into this equation, so what we're saying is that y of t in the impulse response case, when these two things are true, initial condition 0 and the impulse input, that gives us what we're defining as our impulse response, h of t. And so if you look at that, x of 0 is 0, so that goes away. And remember that this is potentially a vector 0 because we could have multiple states. So that makes this whole term go to 0. And then we're going to plug in u is going to be delta. And so if we do that, evaluating this quantity, and then if we put delta also in here, notice if you put delta in here, this actually is 0 because you're not taking the integral over it. The delta functions only has kind of mass or volume inside it if it's within an integral. So this term also goes to 0. So now we're left with this expression. And so the delta function, when you integrate across the delta function, you just pick up the value where tau is equal to this parameter here is equal to 0, whatever's in the inside here. So that's where this is equal to 0, so that just makes it c e to the at b. And so that's the impulse response as a function of time. So that's h of t. And so now if we were to rewrite this state space solution in terms of what we now call the impulse response from state space, I could replace this c e to the at minus tau b, this whole term right here, that could be written as h of t minus tau, because now this, what was t, for h of t, it's e to the at, Now, h of t minus tau would give us this in the exponent. And so if we go ahead and substitute that in here, this says that the general solution of y, which is coming from here, we're rewriting that first equation, same first term, but then now it looks like the integral that we saw before from the transfer function. And so this is not a surprise. And so this connection between this is the time domain, this h of t is the time domain thing that we would take the Laplace transform of to get capital H of S that represents a block. And this represents then the impulse response that is h of t. And so that's how these things are connected. So you can see that the equation that we derived before is still very relevant in the context of the state space equations.